Ugh. Hold on a second. Hold on. Wait. Oh. Sorry. That was tough. I had to go up that hill. And it was a lot of work. Because we all know that going up hills or up inclined planes takes some effort. There's a reason. Because gravity. Right? Gravity tries to make us go downhill. But that's kind of weird to think about. Because if we were to draw a big hill like this, say, well, gravity doesn't pull us this way, gravity pulls us down. Now, gravity goes straight down. That's gravity, Fg. So let's say I was up on a hill, like I just was a second ago when you saw it. If I was up on this hill, gravity would be pulling me straight down, but I end up feeling like gravity's pulling me this way. Actually downward on the hill, down the slope. So how can that be? How can gravity be pulling me this way when I'm on some hill at, let's say, an angle theta? Well, our instinct's correct. It is gravity that's pulling me downhill, but it's not all of that. Gravity is trying to pull me straight down. It can't. So if I'm on a hill and gravity's trying to pull me straight down, it can't. It ends up pulling me kind of down the hill a little bit because that's at least in the right direction. So how can we wrap our heads around this? Well, just like any other vector we've seen, where we go, hey, if it's in an inconvenient direction, we can break it into vectors. Gravity and this hill are in inconvenient directions. They're not either perpendicular or parallel to each other. They're off by some angle theta. That's not really helpful for us. Now, I have a friend, it's actually a relative, my Aunt Eileen, that is great at problems like this. Now, the thing you gotta know about my Aunt Eileen, only 1.5 legs, so she stands like this. So my Aunt Eileen would be looking at this problem, and she would see it this way. And when she looks at the problem, this doesn't look like a hill. This looks flat. But to her, gravity looks like it's going straight up, or it doesn't look like it's going straight up and down. Gravity always looks like it's going at an angle. So she's kind of used to thinking about gravity at some angle. So what she does is she says, all right, let's take gravity and break it into pieces. Just like if we were doing projectile motion, and I said something fires up at this angle, let's break into an X and a Y. She says, well, let's take gravity and break it into two parts. One part that is perpendicular to the plane, and one part that is parallel to this plane. So we'll call this F parallel, we'll call this one F perpendicular. Now, you may be getting dizzy, and I'm afraid I'm going to fall off, so I'm going to take this down again. Okay. So, how do we get from FG to those two? Well, just like any problem with trigonometry, if you have one side and an angle, you're good. Problem is we don't have an angle in here. We have an angle right here. Well, all of you guys are geometry and trigonometry experts. So really quickly, we can do a little bit of mathemagic and figure out the angles inside this triangle. So if this is the ground, it's flat, and gravity goes in the y direction, then this must be 90 degrees. And if this is a right triangle, and that's theta, then this angle here becomes 90 minus theta. So far, so good? Okay. Now this is a straight line. This is a perpendicular line to that straight line. So that side's 90. If this side's 90, then this whole thing here better be 90. Which means what we have left, this little piece in here, is going to be 90 minus this. 90 minus theta. Well, 90 minus theta is theta. So it turns out that this angle and this angle are always the same. Very convenient. Now we can take FG and break it into parts here. So, let's see. This side is to cross from the angle. That theta always looks like an eyeball to me. And I remember this as you see the sign. So this is a part of gravity, and the part it is FG. It's times the sine of theta. The perpendicular component is next to, or with, it's collaborating with the angle, FG times the cosine of theta. Let's get this out of here. All right. Now, we've sufficiently made this diagram really complicated. There's tons of stuff all over the place. It's really messy, so let's simplify it. I'm going to draw a new picture of me on the hill that was on earlier. You saw it. There's me. How many forces are acting on me? Well, there's gravity, sure. But we already kind of said gravity's not convenient in this problem. It's in an awkward direction. These forces are pretty convenient. So instead of writing gravity, let's write these two. Yeah, we're going from one force to two forces, but these are in good directions, so it's easier to work with. So I have a perpendicular force, F perpendicular. I have a parallel force, F parallel. Well, when I was on the hill, I was getting pulled into the hill, but I didn't start sinking because the hill can push back on me. We call that normal force. And it turns out in this problem at least, that normal force is equal and opposite perpendicular force. You know, the hill holds me up. And it holds me up as much as gravity is pulling me into it. So all that's left then is this perpendicular force, or parallel force. Let's say I wanted to know how hard I needed to push myself up the hill so I wouldn't fall. Well, I would say F push equals question mark. But it's not really a question mark, it's just equal and opposite parallel force. Now again, this all may look really nasty, so let's make it easier. If you go back to looking at it like my Aunt Eileen, this is just a normal free body diagram. You know, it's not really complicated. If you could pretend this is the y direction, pretend this is the x direction. We've done that problem 1,000 times. So inclined planes are not complicated, they just kind of look like it. They're not very hard. All you have to do is be patient, break gravity up into these two pieces, and then you have a normal problem to work with. That's it. Hope this helped. Bye.